Myself, K. Sirisha, working as assistant professor in mechanical engineering department in MBR College of Engineering and Technology. Today, we are going to discuss the topic of entropy and clashes in inequality. So, first of all, let us discuss what is clashes inequality. Then, after we will discuss what is entropy. So, first of all, so what is clashes inequality? The second law of thermodynamics leads to the definition of a new property called entropy. So, what is the meaning of that? In second law of thermodynamics, it leads the use the definition of a new property called entropy. So, a quantitative measure of microscopic disorder for a system. Nothing but microscopic is a single particle we will measure. So that is nothing but the microscopic. So microscopic disorder. So that is a quantity of measure microscopic disorder of a system. Entropy is a measure of energy. So which defines what is entropy, which defines is nothing but a measure of energy of individual particles. So that is nothing but the entropy. That is no longer available to perform useful work within the current environment. So to obtain the working definition of entropy, enters the second law. Let's derive the Clausius inequality. So we working definition to obtain the working definition of entropy enters the second law. So we will discuss the entropy and second law. So first of all, we have to derive the Clausius inequality. So when we talk of about the entropy and second law, definitely we will derive the Clausius inequality. Okay, so first of all, let us we start. So consider heat reservoir. This is a heat reservoir giving up heat to a reversible heat engine, which in turns give up heat to the piston cylinder device as shown in. Already we know that. So this is the thermal reservoir. This thermal reservoir gives heat due to the engine. So this engine runs and gives the work done, and rejected heat is given to the system. So here we will run two systems. This is heat engine system, and this is a piston cylinder. Piston cylinder. So we will two works doing at a time. So that we call as combined system. Okay, here we have the system, and in the engine we have a cycle device. So that is a combination of both. So cyclic device, reversible cyclic device is nothing but the engine as a reversible cyclic device. So this is a reversible cyclic device, and we run at the simultaneously with system. So that we call as the combined system. So why you are discussing about the Clausius inequality? If you are talk of about the entropy and second law, so definitely we have to derive the Clausius inequality. So that is okay. So how to derive the Clausius inequality? So first of all, we are before we derive the Clausius inequality. So first we apply the first law of thermodynamics on the incremental basis to the combined system. So combined system, which means we can run at a time of cyclic device and the system. So that is we called as a combined system. So here composed of heat engine and system we called as combined system. So first of all, energy in minus energy out is equal to delta EC. So delta EC is nothing but combined energy. Okay. So here energy in is heat received in reversible minus here work done reversible. Here out is nothing but we look at the diagrams. So here energy in is Q reversible. This is the reversible cyclic device, and this is the system. Here, actually, we have energy in minus energy out is equal to total energy, combined energy. So here, energy in this delta QR minus energy out. Here, various types of energies are out from the system. So this is from actually this is the energy or the work done out from the reversible cyclic device and energy out in the system. So here W reversible cyclic devices work done for cyclic device plus work done for system. Okay, so energy is input of a reversible cyclic device minus energy out is W reversible, that is nothing but energy reversible plus energy of the system is equal to total combined energy of differentiation. Okay, where EC is the energy of combined system, let WC be the work done by the combined system, then first law becomes. So for first law, what do we know? That total energy is equal to total work done. So that is the meaning of first law. What is the first law of thermodynamics? So total energy is equal to total work done, that we called as the first law of thermodynamics. So here, so first law of thermodynamics, how to take this? Actually, W reversible plus W system is nothing but a total combined energy, combined work done. Combined work done. Here, what is the first law of thermodynamics? So difference of difference of delta Q minus delta W is equal to D. But according to the first law of thermodynamics, D is equal to 0. So then after we will discuss. So first of all, if we assume that engine is totally reversible. So totally reversible, then so how do we get delta Q by delta R is equal to TR is equal to del Q by T. So the del QR is equal to TR into del Q by T. The total network done by the combined system is W. Why you taken found that? Actually, del E is 0 here. Okay. So here, so I will discuss it again. En minus E out is equal to delta E. En is this. En is this. Energy in and energy out is the work done of reversible plus work done of system is equal to total combined energy. Actually, according to the first law of thermodynamics, delta Q minus delta W is equal to dE. But first law of thermodynamics, total energy is 0. So del Q or minus del WC is equal to 0. This is WC is nothing but W reversible plus W here. WC is nothing but W reversible plus W system. Okay. So here, according to first law thermodynamics, dE is equal to 0. So what we have finally? Del QR is equal to del W. So del QR is equal to del W. So if the engine is totally reversible, so how can we write the equation del QR by TR is equal to del Q by T? So del QR is equal to TR into del Q by T. If the engine, nothing but this system is also the irreversible and this system also reversible. This system is reversible, this system is. So our total system is reversible. Our equation would be like in the form of del QR by TR is equal to del Q by T. So finally we got the equation in the form del QR is equal to del Q by T into TR. So the total network done by the combined system becomes actually what do you know here? So del QR is equal to del W because of D is equal to 0 according to the first law of thermodynamics. So the total work done by the combined system becomes del C is equal to TR into del Q by T minus DEC. Actually, that step will come. Okay, here. So now the total work done is found by the taking the cyclic integral of the incremental. So the total work done actually here we can replace just the del Q is equal to TR into del Q by T. Actually, this del QR is substitute here. Substitute here. So what is the equation above? So actually this is the equation. Actually, this is the equation. Okay, so this is the equation. So according to the first law of thermodynamics, del Q minus del W is equal to D. So this is the total system, total first law of thermodynamics. And if the system is totally reversible, the formula would be like in the form like that. So this QR is substitute in equation. This is called as equation 1. Okay, this equation we put in equation 1. Okay, put put in equation. So put in equation 1. Okay, so this del QR is put in equation 1 and we get WC. So W reversible plus W system we called as WC is nothing but combined work done. So combined work done is equal to, so this del QR is equal to TR into del Q by T minus DEC. E is the total combined energy. So ultimate combined energy. So that is okay. And next we'll go to the other step. So Here WC is equal to TR into cyclic. Here we apply the integral of incremental work. So del Q by T minus cyclic integral of dE. So actually I mentioned before. So that is for first of thermodynamics, and it is cyclic integral. Cyclic integral d is equal to 0. So and the total work done WC is equal to TR into del Q by T, and this is 0 because of the undergoing it is a cycle. Because of undergo it is a cycle, and energy in is equal to energy is equal to out. What is in and what is out? Because of it is a cycle, it is equal to 0. So WC is equal to TR into del Q by T, and here, have you got the cycle? Have you got the Clausis inequality? If work done, combined work done is positive, it violates the Kelvin Planck statement of the second law of thermodynamics. Second law of thermodynamics. So, if it is violated, so nothing but our work done, our combined work done, if it is a positive, and the Kelvin Planck statement of second law is violated. If it is violated, we cannot do two works at a time. So, we want to run at a time. So our combined work done can be 0 or negative. If negative or 0, and we get and it does not violate the Kelvin Planck statement of the second law. So, but our temperature TR greater than 0, absolute temperature TR greater than 0. Finally, our combined work done is equal to TR into cyclic integral of P cube del Q by T less than or equal to. So you have to remember only according to the Clausis inequality what it is. Cyclic that is the combined work is equal to TR into, and cyclic integral of del Q by T less than or equal to 0. So our work done, combined work done, del Q by T less than or equal to 0. Only we have 0 and negative values. We got if it does not violate the Kelvin Planck statement of a second law of thermodynamics. If our combined work done is positive, it violates Kelvin Planck statement of second law of thermodynamics. So finally, I want to clear one thing that our WC is equal to TR into cyclic integral of del Q by T, or del Q by T is less than or equal to 0. We have only 0 and negative values has occurred in Clausis inequalities, and temperature, absolute temperature is greater than 0. So that is Clausis inequality. Finally, what I clear that our cyclic integral of del Q by T is less than or equal to 0. We got the values of negative and positive values only. Okay, so and next, so here our cyclic integral of del Q by T less than or equal to 0. So I finally mentioned that our cyclic integral of less than or equal to 0. So our Clausis inequality states that the values we have only 0 and negative values. Here Q is the net heat added to the system. So our cyclic integral of Q net by T less than or equal to 0. So this equation we call it as Clausis inequality. The equality holds for reversible and process, and inequality holds for a irreversible process. So that is nothing but if del Q by T is equal to 0, that equation we call as reversible process. If our the cyclic integral of del Q by T less than or equal to 0, so that we called as a irreversible process. Is equal to 0 for reversible process, less than or equal to 0 for irreversible process. Here one problem is there, and it is what is inequality? Inequality is nothing but less than or equal to cyclic integral of del Q by T less than or equal to 0. So that is we have only 0 and negative values. Okay, we will look at one problem, then after we will understand everything what is about the cyclic process. For a particular power plant, the heat added and rejected both occur at constant temperature, and no other process experience any heat transfer. The heat is added in the amount of, that is nothing but Q1 and T1, and rejected amount of 1950 kilojoule and 20 degrees. That is nothing but Q1 T1 and Q2 T2 is the Clausis inequality, or hint is Clausis inequality satisfied, and it is the cyclic reversible or reversible. We can tell if it is a cyclic reversible or irreversible. First of all, what do you know about the Clausis inequality? The Clausis inequality is less than or equal to. So cyclic integral of del Q by T less than or equal to. That is the meaning of we got the values of 0 and negative values. That is a Clausis inequality. Then after we will proceed this cycle is reversible or irreversible. So look at, okay, what do you know the Clausis inequality? Cyclic integral of cyclic integral of q net by del q net by t less than or equal to 0. So this is we call as Clausis inequality. Why we take q net? Because of we have two heat transfers. Okay. So first of all we apply the integral. So integral of two sides, because of in and out I can take. So del of q net by t in plus del of q net by t less than out less than or equal to 0. Q net by t, because of with integrated, so we got only the q net by t in plus q net by t out less than or equal to 0. Just remove the del by adding with the integration. So we're doing with integration, and the del is gone, and we got the only q net by t in plus q net by t out less than or equal to 0. So q net by t plus q net by out. Why you are here? Why you are taken as negative? Because of our problem is mentioned that and is rejected. So when we have any loss rejected is mentioned, that is that the heat transfer takes place is negative. Okay, that heat transfer will take place negative. So so our q net is negative. So q out by t. So q in by t in plus q out by t out. So our q is nothing but rejected. So less than or equal to 0. Finally, what we have, Q1 is 3150, T1 is 440. So we will be convert in the form of Kelvin, in the form of 273. Here also 20 plus 273, and just replace here. So Q in by Q out, Q in by Q out, Q in by Q out. So here Qn is 3150 kilojoule by 440 plus 273. Because of we will be changed in the form of degree centigrade to Kelvin state Kelvin. So 440 plus 273. Here Q is rejected. So that is Q out is minus 1950 kilojoule by 20 plus 273 less than or equal to 0. So finally we got a minus 2.237 kilojoule per Kelvin less than or equal to 0. So what I said, so our less than or less cyclic integral of Q by T less than or equal to 0. That is meaning of we got only 0 and negative values. So now we are going to calculate the efficiency. Calculate the network cycle efficiency and Cornet's efficiency based on TH and TF for this cycle. What do you know the work done? Work done net is Q in minus Q out. Q in is 3150 and Q out is minus 1950. Got the 1200 kilojoule. And what is the thermal efficiency? Output by input. Output is work done and input is Q in. So output is 1200 kilojoule, but Q in is 3150, and finally we got the efficiency of 38.1%. And what do you know of thermal efficiency of Cornet cycle? So efficiency of Cornet cycle is 1 minus TL by TH. TL is nothing but lower temperature and TH is nothing but higher temperature. And just put the values, and our temperature is taken in the form of kelvins only, and just we add degree centigrade with the 273 and got the it will be correct in the form of Kelvin. 1 minus 20 plus 273 by 40 plus 273 and got 58.9%. Okay, so here we can observe one thing here. So this is absolutely irreversible. Why? Because our here Cornet efficiency is 58.9% and the thermal efficiency is 38.1%. So our Cornet efficiency is greater than the thermal efficiency. So definitely it is a reversible process. Irreversible process. Okay. And next we go to sorry. So this is the also the same that so definitely we have got a 38.1% and finally we got irreversible process. And next we go to the another problem. The Clausis inequality is satisfied. The Clausis inequality is satisfied since the inequality is less than 0. Since the inequality is less than 0. Here we can observe that this inequality is this value minus 2.237 less than or equal to 0. So that is the value is less than 0. Okay. So that value is since the inequality is less than 0, the cycle has at least one irreversible process, and the cycle is irreversible. One way our efficiency is compared with the Carnot efficiency, it is less than the Carnot efficiency, so our process is irreversible process. Okay. And next, for a particular power plant, the heat added and rejected both at constant temperature. No other process experience any heat transfer. The heat is added is almost 3150 kilojoule and 440 degrees centigrade, and rejected in the form of 1294.46 kilojoule and 20 degrees centigrade. Is the Clausis inequality satisfied, and is the cyclic reversible error? Same process, we can do the problem, and I will explain again. So what the previous problem is solved, that is the same problem. So cyclic integral of del q by t less than or equal to 0. Same like in and out less than or equal to 0. Q in by t in plus minus of q out by t out, and just substitute the values here, and this value also got the same like that, and here also the same thing, and W net and the thermal efficiency. So we got the irreversible process only. So these are all the classes. Next topic we will uh, we will consider the what is entropy. Okay, thank you, students.